One of the key principles of any truly object-oriented design is polymorphism. Polymorphism literally means many shapes, and it's actually a pretty straightforward concept. It refers to the idea that a class can take on many different shapes. To get at the idea that a class can take on many shapes, we need a class hierarchy with inheritance, basically a superclass that's specialized into multiple subclasses. So, the idea is that the superclass, the one higher in the class hierarchy, can take on the particular form of any one of its subclasses. That is, the superclass can have many different shapes, each of which are examples of the overall class. To give the superclass this kind of flexibility, we'll be defining what are known as virtual functions. Basically, virtual functions will be ones that get defined differently. That is, they take on a different shape in all of the child classes. The important part of polymorphism is that we can define operations at the highest level of the hierarchy where it makes sense. Basically, we define an operation on the top-level superclass as much as possible. Then, the actual implementation of that operation can be defined at any point along the hierarchy. Each of the subclasses could potentially have a different way of performing that operation, but they all perform it. When we refer to some class, then anything that is of that class, including any descendant classes, could meet the requirement. For instance, we could have a general vehicle class with subclasses like car, SUV, pickup truck, and so forth. If we had an operation to do, like transport a chair, the three vehicles would do that in different ways. It would go in the bed of the pickup, and it might have to be tied to the roof of the car. But the key is that any vehicle could do that. I could perform the transport a chair operation with any of them, even though they implement the operation in different ways. Now, inheritance can save coding by inheriting features from a base class rather than having to repeat them in all of the derived classes. But probably an even more important feature of inheritance is that it supports the ability to let classes lower in the hierarchy meet the requirements defined higher in the hierarchy. The idea of a class hierarchy means that when a function is written to use some class, that same function can also use any of its descendant classes. For example, imagine that we had an animal base class, and we had derived classes for zebra, elephant, giraffe, and so on. We could write a function that takes in an animal parameter, and that function would be able to accept a zebra, an elephant, and so on, since those are all examples of animals. However, things don't work the other way around. We can't require a more specialized class and pass in the more generalized superclass. If we have a function that requires an elephant parameter, we can't just pass in any general animal. That's an example of animal polymorphism. Let's look at a quick example in code, going back to our product, cup, measuring cup, and drinking cup hierarchy that we used when describing inheritance. As a reminder, we defined a base product class and derived cup and plate subclasses from that. Then, from cup, we derived measuring cup and drinking cup. In this case, every member is public, just to make the illustration easier. The product class had a retail price and a wholesale price. Now, say we wanted to create a function that put items on sale, say by 10%. We might want a function that gives us the sale price. So we can write a function sale price that returns a floating point number giving the sale price. And it will have one parameter, which will be a product. And it will just return 90% of the product's retail price. Then, we can create very specific objects in our code. In this case, we've got a plastic cup that's an instance of measuring cup, and we've got a coffee cup that's an instance of a drinking cup. Since both the measuring cup and the drinking cup are derived from the product class, we can call the sale price function on both of them without difficulty. Now, this is one of the most straightforward ways that we can use polymorphism. When we inherit from a base class, we automatically have access to everything that that base class has. That is, the descendants from a base class have all the member variables and functions from the base class, and so any descendant can be used in place of that base class. This makes it possible to extend an existing class to provide more functionality. We add on some additional features that we might want, and we keep everything about the class that we already liked, including how it could be used in functions. Let's look at one of these situations where we extend an existing class a little more closely. If you remember the exceptions we discussed for getting out of functions when we have errors, you remember that we talked about different types of exceptions. Well, the way this works is that there's a base exception class. Then there are a lot of classes that are derived from that. Some are derived directly from exception, like bad alloc, logic error, and runtime error. And some are further derived from there, such as out of range being derived from logic error. As for our try-catch statements and exception throwing functionality, though, it's designed to work with the general exception class. So, all the various specific exceptions can be used in any function that takes an exception as input, since they all inherit from exception. And we can even create our own exceptions. Let's say that we wanted to create a new version of a logic error, one that we can use to report when there's a bad value. And say that we want to keep track of that value within our exception itself. Let's see how we can do this. In this example, we've defined a new class, bad value exception, that inherits from logic error. The class does just a few things. First, it has a private member integer variable value that will be used to store the bad value that was used. It has a constructor that takes in an integer and a string, with the string having a default value of the empty string, so that the constructor could be called with just an integer. The constructor uses the string to initialize the logic error base class. And it uses the integer parameter to set the value member variable. Finally, our new bad value exception class has a public member function printVal that just prints that stored value. So basically, this class is now our very own special exception that we can throw when we want to and use how we want. Next, we have a function defined, something to do, that has one input parameter. For some values of the input parameter, those less than 3, it will print a message, and for others it will throw our bad value exception. That's all. In the main function, we have a try block, where we call the something to do function with 3 different parameters. The first call will be a good value, so it will just output an output statement normally, no exception is thrown. The second call, though, causes one of our bad value exceptions to be thrown. So in our catch block, we have a catch defined to take a bad value exception. And for that, we use the printVal function to print the value. When this is run then, we get one line output from the something to do function, and then another line printed from the printVal as part of the exception catching. Now, there was no reason that we had to make bad value exception derived from exception. We can actually throw and catch things other than exceptions. But if we modified our code just slightly to make it more general, where instead of catching just a bad value exception, we catch a more general exception and output a general statement, we see that this still works for our bad value exception. That is, because we made our new class derived from logic error, which is itself derived from exception, we can use it in all the ways that we would have used an exception. Plus, if we ever want the special functionality that logic error could provide, we have that too. Now, what's relevant to keep in mind here is that we can define our own more specific exceptions that we can potentially make more use of than the base exception. And this goes for just about any class there is. If we have a class and we want to make a more specialized subclass from it, we can just inherit from that base class. And we start out with everything that it had, and then can add on additional features that we want our new class to have. We haven't eliminated ourselves from using any of the stuff that was already in place for the base class that we derived from. But polymorphism can do even more than just let us use inherited classes. With polymorphism, we also have the ability to create member functions of classes that operate differently but can be called the same way. So, a base class declares some function, and possibly even provides an implementation, a full definition for that function. Then, a class that's derived from that base class creates a slightly different version of the same function. Here's how this works. Say we have a base class and a derived class. Let's say that there's a function a defined in the base class. And say that the derived class also has a function a defined. Then let's imagine that we have code that defines a function, fun, that takes in a base class as a parameter, and that then calls the function a on that parameter. When we call the function fun with an instance of base class, then it will call the function a that's defined in the base class. On the other hand, if we call fun with an instance of derived class, then it will call the function a that's defined in the derived class. Let's look at a simple example of a class hierarchy that will help support polymorphism. I'm first going to show you a setup, but the setup doesn't yet support full polymorphism. So in this case, imagine that I'm a car dealer. I'll have access to a general class to keep track of cars, and then from that I'll derive classes that represent the more specific cars. So in this case, I have a base car class that contains two member variables, a base price and a model name. I'll also have a class for the SC300 model car, which inherits from the car class. That class will have three member variables that are Booleans, indicating whether the car has various add-on features specific to that car, like a performance or entertainment package. Now, each of these classes will also have constructors defined. For the car class, there will be both a default constructor for a generic model car and a constructor allowing the base price and the model name to be set. For the SC300 class, the constructor will take parameters specifying whether or not the various options were ordered. It will call the car constructor with the base price for the SC300 and the model name for the SC300, and then we'll set the appropriate Booleans. Now, the interesting situation will be the member functions defined, where there will be functions with the same name but different behavior. Both the base car class and the derived SC300 class will have two functions, one giving the price and one that prints information about the vehicle. For the car class, the price is just the base price, and the only thing to print is the model name and price. For the SC300, the price is determined based on which optional packages are included, and the output will be more complicated. Now, if we create a generic car just using the default constructor for the car class, and we call printinfo for that object, it will print the version of printinfo defined in the car class. If we instead create an SC300 car, and we call printinfo for it, we'll be calling the printinfo function defined in the SC300 class, not the one defined in the car class. Okay, is that polymorphism? Well, all we're really doing here is letting subclasses do some redefining of functions from superclasses. A complete version of polymorphism comes from the superclass, where a single function from the superclass is created that takes on different forms in the subclasses. I'll show you a modified version that really does demonstrate polymorphism, and then we'll look more closely at the details. The code here has a few changes from the previous code. First, notice that in our base class car, we now have the word virtual in front of our two member functions that we want to override in the base class. The virtual is actually needed to say that this function will be a polymorphic function. Next, we've defined a new function called printCar. This function takes in a car parameter as a reference and just calls printinfo for that car. It's important that the parameter is a reference here, as we'll see in a second. Our main code is also modified so that we're calling the printCar function, passing in a car and an SC300, rather than calling the member functions for each. Other than that, this code is the same as before. Now, when we run this code, we indeed see that the specific versions of printinfo are called. That is, when we call printCar with a car object, it will end up calling the printinfo command defined in the car base class. And when we call printCar with an SC300 object, it will end up calling the printinfo command defined in the SC300 class. This is exactly what we want from polymorphism, the ability to define a different version of a function for different classes. This way, when we call printCar, we get the most descriptive output that we can. Now, to see how the syntax works, let's see what happens if we remove the virtual from in front of the declarations in the base class. When we run this code, we see that the output when we pass in the SC300 object is just the printinfo result for the car class, not for the SC300 class. We know this because we're not seeing the printout of the various options, and the price is only the base price, not the price with options. Now what's happened here is that we no longer have a polymorphic function. Instead, the calling function printCar says, I have a car object, and so I will call the car object's printinfo function. Without the virtual statement, it won't look to see if this function has been overridden by a subclass. It's a different situation than earlier when we were calling printinfo directly on an object. There, we knew that we were calling the function from an SC300 object. So we would first look at the SC300 definition to see if printinfo is defined there. And if it is, like it was in this case, we would have used that. And only if it was not defined would we look at the parent to see if it had printinfo, and so on. But in this case, we're in a function where we think we have a car object. And so the compiler is going to look at the car class, and it's going to find a printinfo function defined, and so it'll use that. It isn't going to look farther to see if the function has been overridden, since it was not declared a virtual function. So, if there's a function that you want to allow to be polymorphic, that is, you want to allow a subclass to override and provide a more detailed description of the function than in the base class, you should always make sure it's declared to be a virtual function. It's simple enough to do. Just put the keyword virtual in front of the definition. Now, it's worth noting that subclasses don't have to redefine the function if it's virtual. It just means that they have the option of redefining it if they want to. Okay, let's look at one other variation, with the virtual back on these functions so that they're indeed polymorphic, and so that the subclasses can redefine the function if they so choose. But now, I'm going to change the printCar function to take in a parameter by value instead of by reference. That is, instead of the parameter being car ampersand C, I just have car C. Again, the output shows that the printinfo function that's called is the one for the car class, not the one for the SC300 class. But it looked like we declared this as virtual, so what happened here? Well, here's what's going on. In the earlier case, we create an SC300 object in our main code, and we pass this to the printCar function using a pass by reference. So what happens when this function is called is that the memory for the parameter has a reference stored. This is basically a pointer, and it refers to the object that was passed in. No data is copied. We just have a reference to the object that was passed in. Since the SC300 class is derived from the car class, it's okay to pass in the SC300 as a reference. So, when we call printinfo within the printCar function, we go to that reference and we call printinfo on it. And since the thing it's referring to is the SC300 object that was created before, it will try to call the printinfo command for the SC300 object. Since printinfo was declared to be virtual, it will look for the most specific version of the printinfo function, which is the one defined in the SC300 class. Now, on the other hand, if we pass by value, here's what happens. We still have an SC300 defined in the main program that we call printCar on, but now it's a parameter that's passed by value. So when the function is called, there's a space set aside in memory for a car object. Then the values from the argument are copied into the car object that's been allocated. So in this case, that's the base price and the model name, which were defined in the car class, but not the various booleans that indicated which packages were selected. The thing that's sitting there in memory is a car, not an SC300. It has no memory of having originally come from an SC300. All it knows is that it's a car. And as a result, when we call printinfo on that object, it's going to use the printinfo command defined for the car class, not the one defined for the SC300 class. So, let's review. When you want to use polymorphism in function definitions, what are the two key things to remember? One, you want to declare as virtual any functions that you want to be able to override. And two, you want to pass parameters by reference so that they don't get copied into smaller classes. Declare virtual functions and use pass by reference. Now, it's possible for the base class to declare a virtual function yet provide no definition. And this is what's known as a pure virtual function. Declaring a base class without a definition has some major implications for the class itself. Let's illustrate this with an example. In the code you see here, we're providing classes that can be used to calculate shipping costs for a package. To keep the illustration simple, our class will have no member variables and just one member function, which is named shipping cost. We have one base class, the shipping company. And this is going to be a class that the other classes inherit from. In the shipping company class, we declare one member function, shipping cost. Now, there are a couple of things to notice about this function declaration. The shipping cost function is declared virtual, as we would expect, and it has a return value float, and it takes in a single float parameter. Now notice that our parameter does not have to have a name declared because we're not actually defining the function here. Instead, this is going to be a pure virtual function. And the way we designate that is that instead of providing the function definition, that is, instead of having a body enclosed in curly braces, we instead just write equals 0 semicolon. That equals 0 is the way of designating that this is a pure virtual function. A pure virtual function will have to be defined in the derived classes. So in this case, we have 3 different specific shipping companies, and each of these will define its own version of the shipping cost function. First, we have very quick transport, or VQT. For VQT, the shipping cost will be a base cost of $3 plus an additional cost of $1.50 for each additional unit of weight. The next class derived from shipping company is NatFast, and this class defines shipping cost as just directly proportional to the weight, $2 times the units of weight. And a third class derived from shipping company is Government Post. This class defines shipping cost by having fixed price tiers below a certain weight level. The key thing to realize is that the base class, shipping company, declared a pure virtual function with no implementation. Only in the derived classes were actual definitions for that function given. Now, just to illustrate how this might be used, we'll have a function called selectCompany that asks a user which company they want to use for shipping. And depending on the choice, a new version of a VQT, NatFast, or Government Post will be generated. In this case, a new object of the appropriate class is allocated dynamically, and a reference to this new object is returned from the selectCompany function. That is, the function returns a shipping company ampersand, and the return command will be return star new, and then the class name followed by parentheses. The new class name parentheses creates a new object of that type on the heap, which is given as a pointer, and the asterisk lets us refer to the object itself. Since we're returning a reference, we're getting a reference to the actual object created. Notice that we're returning a reference to a shipping company, the base class. Since the three possible objects that we create are all derived from shipping company, a reference to any one of them will still be a reference to a shipping company. But we need to return a reference, not an actual shipping company, since the shipping cost function is defined only in the derived classes. Now also notice that this is another way that we can make use of pointers and other ways of referring to memory directly. If we have a pointer, it can be a pointer to a base class, even if the thing underneath is one of the derived classes. In our main routine then, we can get the package weight from the user. Then we can use the select company function to get a reference to a shipping company. Notice that we don't need to know which shipping company it is in the main routine. We just have a reference to some shipping company. And then we can call shipping cost on that shipping company to calculate the cost. Now, when we have pure virtual functions, it's important to realize that we can't just have an instance of the base class. In the previous example, it doesn't make any sense to have just a shipping company. There's no way to know what the shipping cost would be for some generic shipping company. Instead, we need to have a specific shipping company, like VQT or NatFast or Government Post. So, the term we use to refer to a class that has pure virtual functions is an abstract class. It's abstract in the sense that it defines a general idea, like shipping company, that can't refer to any specific instance of the class, but it rather just defines some more general abstract representation. We can't create an object out of an abstract class, though as we just saw, we can have references to an abstract class. Classes that do provide the implementation details, the lower level derived classes that we can create objects from, like VQT or NatFast or Government Post class, those are sometimes called concrete classes. So notice, if we take the same earlier definitions and we change our main routine to try to create an instance of a shipping company, what we end up with is an error telling us that we can't declare an abstract type. Let's try one of the classic examples that's often used to show how inheritance and polymorphism work. Try this yourself. Try to create an abstract shape class that has an area function. Then create two specific concrete classes, square and circle, that inherit from the general shape class. Here's the way this could be implemented. We first declare a shape class. This will be an abstract class, and it will have one pure virtual function, area. Area will not take any parameters, and it will return a float, giving the area of that shape. Now notice that area has to be a pure virtual function, since we can't compute the area of some general shape that we have no information about. And so the shape class is an abstract class. We won't be able to create a shape object, but we will be able to derive classes from shape. Then we'll have two derived classes. For square, we'll have a private member variable side length. And we'll also have a constructor so that we can declare specific instances that have a given side length. Then we have our definition of area for a square, which is just the square of the side length. We have a second derived class named circle. In this case, the private member variable is radius. We again have a constructor, which in this case just sets the radius of the circle. And we have an implementation of the area function. For this area function, we compute pi times the radius squared. So, we have a general category, shape, that's an abstract class, and we have two concrete classes that derive from it. And you can easily imagine ways that we might extend this. We might include more shapes, like triangle. Similar to square and circle, we would just declare triangle as a subclass of shape, and it would store the lengths of the three sides and provide a constructor. And since this is a concrete class, we'll need to provide an implementation of the area function for it also. As another extension, we could add another virtual function, perimeter, to the shape class. And that means that we'll have to provide implementations of perimeter in all of the concrete classes that we derive from shape. And we could implement functions that just take a reference to a shape as a parameter. So in this case, I defined a reportInfo function that will take in a shape reference. Then that function will be able to use all the member functions like area and perimeter that are defined in the concrete classes. In this case, reportInfo will call the area function to report area and the perimeter function to report perimeter. The implementation from whatever actual concrete class was passed in is used, so we will get the result from square, circle, or triangle. At this point, we've now seen the key features of object-oriented programming. We can approach problems by defining classes that exhibit encapsulation, inheritance, and polymorphism. We can think first in terms of inheritance, how classes are related to each other and what hierarchy they should form. And we should consider for each class how it should encapsulate the data and functions that it provides, including what elements should be public, private, and protected. And we can look for ways to take advantage of the flexibility of polymorphism. The child classes all inherit one or more common goals by way of virtual functions, but each child reaches those goals by applying its own particular talents in its own unique way. In our next lecture, we'll be bringing all of that together as we face the task of developing a larger scale program using an object-oriented design. See you there.